My name is Jason St. Clair. I work at NASA's Goddard Space Flight Center, and I'm here in Kansas doing the DCOTS project. And DCOTS, I think a lot of other people have already talked to you about, but it's a project where we're studying convective thunderstorm transport up into the stratosphere and what that does to the chemistry and humidity of the lower stratosphere. Our part, the Goddard role in this campaign, is we've got 3 different instruments on the aircraft. One measures ozone, it's called ROSE. One that measures NO2, which is the one here. It measures, well, NO2. And then we have a similar instrument on the other wing pod that measures formaldehyde, and that one's name is CAFE. And so those 3 instruments make measurements of compounds that are of relevance to the science that we're trying to do. This one in particular, NO2, it's something that comes out of automobile exhaust, but it's also formed through lightning, and so these thunderstorms with a lot of lightning can produce NO2 that gets moved up into the stratosphere. There's also a lot of NO2 in the stratosphere anyway, so as we try to understand where the air is coming from and what chemistry is happening, having an NO2 measurement is really helpful. ROSE with the ozone measurement, obviously we think about the stratosphere and the ozone layer and how it protects us from UV rays so we don't get skin cancer, and so that's a very, very important measurement for this campaign as well. CAFE on the other wing, formaldehyde is something that we think about maybe preserving frogs that you dissect in your high school biology lab, but it's also something that's produced when any organic compounds in the atmosphere get oxidized. So when they get chewed up in the atmosphere, they make some formaldehyde, and we can say, hey, there was some oxidation of organics going on right there. And so in this case, down where we live, there's a lot of emissions from trees and power plants and all that. As those emissions get oxidized, we can tell the air came from the lower part of the atmosphere up high because there's formaldehyde that got moved up with it. Formaldehyde doesn't last very long in the atmosphere, so if you see it up in the lower stratosphere, you know it just came up with a big thunderstorm. So that's why we want to measure formaldehyde. So other than that, it's a great opportunity to be working on this amazing airplane and with just a world-class set of scientists.
Now, what are the long-term effects if there's like formaldehyde, for example? Why does it matter if it's in there?
The formaldehyde itself doesn't matter too much. It does affect the chemistry because formaldehyde, when it's hit with UV light, will make OH radical, and that's a major oxidizer in the lower stratosphere. OH radical is actually one of the main destroyers of ozone in a natural process. But if you start producing more water, more formaldehyde up there, you can actually perturb the chemistry a bit, and it's just processes that we want to understand. I think for this campaign specifically, the formaldehyde is a really good tracer to tell us, hey, this air used to be down in the troposphere, down where we live, just a few hours ago, and now we're seeing it in the stratosphere. So it's a clue that we just had recent air coming up. In addition, one of the things we've been trying to figure out in this project is we've had campaigns previously where we saw elevated water, and the question is it just water that's coming from ice crystals that evaporated, and so not a whole lot of air that we think about as air is going up? It's mostly just going up as ice crystals and then melting and making water? Or is it water going up with a whole bunch of air along with it? So if we see formaldehyde, we know that there's a whole bunch of tropospheric air coming up. If there's not a lot of formaldehyde, only just a bunch of water, we know that it was mostly just ice.
Why do we not want to experience ozone at the ground?
Right, that's a great question. Yeah, so ozone up high in the stratosphere with the ozone layer is really important for protecting us from strong UV light that would give us skin cancer. Down here, we don't want it because if you breathe it, it's really bad for your lungs. And so the EPA, when they try to regulate air quality, there's 2 main things that they care about that are bad for us. Those are ozone exposure and particulates. And so particulates are little tiny invisible things that float through the air and can get embedded in our lungs. If you breathe in ozone, it really damages your lungs too. It can cause asthma attacks, things like that. And so when you think about like smog, I grew up in the Los Angeles area, and everyone knows LA has smog. Smog is mainly those 2 things. It's photochemical ozone, meaning photochemical, it wasn't emitted, it was things like NOx that were emitted, and then chemistry happens with light and you make ozone. And so that's what photochemical ozone means. So photochemical ozone and particulates, either directly emitted like out of a smokestack or a diesel truck, or that chemistry that made the ozone can also make some what's called secondary organic aerosol, where you took gases in the atmosphere, reacted them, and then they made the little particles that you don't want to breathe.
How are you measuring? How does this instrument actually measure?
Oh, that's a good question. So with this instrument, with the canoe instrument, what it does is it brings in air through an inlet here into the instrument, and it ends up hitting that air that's coming in with a laser. That laser is a specific wavelength. This one is a green laser. It's 532 nanometers. And when it hits NO2 molecules, some of those NO2 molecules absorb that light, and then they glow. They fluoresce at a different wavelength that we then detect. So they glow in the red into the infrared, and we detect those photons, and that tells us how much NO2 is in the sample. CAFE is a similar technique, but it uses a UV laser instead of a green laser. And Rose back there doing the ozone is a different technique. It has an LED, a light emitting diode that emits UV light, and then we send it into a little cell that has really reflective mirrors on it. And so most of the light doesn't make in, but what does get in bounces back and forth a lot. And what that does is it gives us extra sensitivity because it spends more time going through our sample before it hits our detector. And so that's just a more normal absorption measurement, but with an enhancement with the fancy mirrors.